There is a planet that should not exist. Not in the way that hot Jupiters shouldn't exist, or diamond planets shouldn't exist, where the surprise is a violation of our formation models. This is different. This is a planet that watched its star die, that survived the expansion of a red giant that should have consumed it, that orbited through the death of its solar system and came out the other side, still intact, still moving, still there. Its name is WD 1856 plus 534b. It orbits a white dwarf, a dead star, in the constellation Draco, approximately 80 light-years from Earth. It is roughly the size of Jupiter, and it completes one orbit of its dead star every 34 hours. 34 hours. It is so close to the white dwarf that it orbits inside the region where the white dwarf's progenitor star, the living star that existed before death, would have extended during its red giant phase. The planet is orbiting inside the ghost of a dead star, inside the space that the expanded stellar envelope once occupied. Either it was not there when the star died, or it survived something that physics says it could not have survived. Both possibilities are extraordinary. One of them is true. We do not yet know which. To understand why this planet's existence is so difficult to explain, you need to understand what happens when a star like our Sun dies. A medium-mass star, anything between roughly half and 8 times the mass of our Sun, spends most of its life on what astronomers call the main sequence. It burns hydrogen in its core, converting it to helium, releasing the energy that makes it shine. For our Sun, this phase lasts approximately 10 billion years. We are currently halfway through it. When the hydrogen in the core runs out, the core contracts. The outer layers of the star expand dramatically, not slowly, not gradually, but on astronomical timescales that are nevertheless catastrophic for anything nearby. The star swells outward, its surface cooling as it expands, transitioning from yellow to orange to red. It becomes a red giant. For our Sun, this expansion will carry the surface out to approximately 250 times its current radius, far enough to engulf Mercury, far enough to engulf Venus, possibly far enough to engulf Earth. The inner solar system will be consumed by the dying Sun, scorched, evaporated, absorbed into the stellar envelope. This is the standard picture. It is well understood. It is confirmed by observations of red giants across the galaxy, and it is exactly what should have happened to any planet orbiting close to the star that became WD 1856 plus 534. The white dwarf's progenitor was a star of approximately 1.5 solar masses. When it died, it expanded into a red giant and then a larger, cooler asymptotic giant branch star before shedding its outer layers and leaving the white dwarf behind. During those expansion phases, the star's radius extended to approximately 1 to 2 astronomical units from its center. WD 1856 plus 534b currently orbits at approximately 0.02 astronomical units from the white dwarf. That is inside the region the dying star occupied. When this planet was discovered in 2020 by NASA's TESS satellite, a space telescope designed to detect planets by watching them pass in front of their host stars and briefly dim the starlight, the detection was straightforward. A small dip in the light from the white dwarf, repeating every 34 hours, the signature of a Jupiter-sized object passing across the stellar disk. The detection was straightforward. The existence of what was detected was not. The team that confirmed the planet, led by Andrew Vanderberg at MIT, immediately confronted the problem. A planet at 0.02 astronomical units from a white dwarf is a planet that during the red giant phase of the progenitor star was inside the star. It was orbiting inside the stellar envelope. It should have experienced drag from the surrounding gas, lost orbital energy, spiraled inward, and be destroyed, consumed by the expanding star, or torn apart by tidal forces as it fell toward the core. except it wasn't, except it's there. There are two frameworks for explaining how this happened. They are not mutually exclusive. One or both may be partially correct. Neither is fully satisfying. The first is survival. Perhaps WD-1856 plus 534b was inside the red giant envelope and survived. Perhaps the interaction between the planet and the stellar gas, rather than causing the planet to spiral inward and be destroyed, caused the planet to spiral inward just enough, losing orbital energy to the surrounding gas to end up in a tighter orbit without being consumed. This process is called common envelope evolution. It is a real mechanism. In binary star systems, when one star expands and engulfs its companion, the companion can interact with the envelope in a way that ejects the envelope entirely. The orbital energy of the spiraling companion is deposited into the envelope, and if there is enough energy, the envelope is blown away, leaving the two objects in a much tighter orbit than they started in. Could a planet do this? Could a Jupiter-sized object spiraling through a stellar envelope deposit enough orbital energy to survive the process? The numbers are difficult. A planet is much less massive than a stellar companion. Its total orbital energy may not be sufficient to eject the envelope. It would need to spiral inward very rapidly before being ablated by the heat of the surrounding gas, before tidal forces tore it apart, before the density of the envelope slowed it to the point where it could not complete the in-spiral. The simulations are not encouraging. Most of them suggest that a Jupiter-sized planet entering a red giant envelope is destroyed, not quickly, but inevitably, over a period of thousands of years, as it slowly loses energy to the surrounding gas and spirals inward to its death. Most, not all. Firmly, some parameter combinations allow survival. Some configurations of planet mass, orbital parameters, and envelope density produce outcomes where the planet spirals inward and survives in a tight post-common envelope orbit. It is possible. It is not the most likely outcome. But WD-1856 plus 534b is there, and possible is all it needs to be. Thinking. The second explanation is migration. Perhaps WD-1856 plus 534b was not inside the red giant at all. Perhaps it formed further out, at several astronomical units from its star, safely outside the range of the stellar expansion, and migrated inward after the star died. Precisely, the mechanism for this migration is gravitational scattering. When a star dies and becomes a white dwarf, it loses approximately half its mass during the red giant and asymptotic giant branch phases. That mass loss changes the gravitational environment of the surviving planetary system. Planets that were in stable orbits may find their orbits destabilized by the changed gravitational balance. They interact with each other gravitationally, exchange energy and angular momentum, and some are scattered onto new trajectories.
A planet scattered onto a highly elliptical orbit, one that passes very close to the white dwarf at its innermost point, can then have its orbit circularized by tidal interactions with the white dwarf over many orbits. The close approach produces tidal forces that dissipate energy, gradually shrinking and circularizing the orbit until the planet ends up in a tight, nearly circular orbit at a distance of 0.02 astronomical units. This mechanism works. The timescales are long, potentially hundreds of millions to billions of years, but the physics is established. We see evidence of planetary scattering in polluted white dwarfs, where the heavy elements in the atmosphere are the chemical signatures of disrupted planetary bodies that were scattered inward after the star died. But direct scattering of a Jupiter-sized planet onto a stable, tight orbit is not easy. The geometry has to be right. The timing has to be right. The mass of the scattering bodies has to produce the right kind of deflection. Again, possible, not straightforward. Here is what makes WD-1856 plus 534b important beyond the puzzle of how it got where it is. It is the first giant planet ever confirmed orbiting a white dwarf. Not a candidate, not a statistical inference, a confirmed detection. A transit signal, repeating precisely, geometrically consistent with a planet of approximately Jupiter's size. White dwarfs are the endpoints of the stars most likely to host habitable planets. Sun-like stars, which make up a substantial fraction of stellar populations, all become white dwarfs. If planetary systems can survive the death of their stars, if planets can remain in orbit around white dwarfs, particularly in or near the habitable zone of the white dwarf, then white dwarf planetary systems become a new category of potentially interesting environments. The habitable zone of a white dwarf is unusual. White dwarfs are dim, much less luminous than main sequence stars, which means the habitable zone is very close in, but it exists. For a typical white dwarf, a planet in the habitable zone would orbit at roughly 0.01 astronomical units, similar to the distance of WD 1856 plus 534b from its host. WD 1856 plus 534b is a gas giant. Not habitable itself in any standard sense, but its existence establishes that planets can exist at the orbital distances where white dwarf habitable zones sit. That the destruction of the star does not inevitably destroy all nearby planets, that something can survive. In restrained, if smaller planets, rocky planets, can survive or migrate to white dwarf habitable zones, then white dwarf systems may host the oldest potentially habitable environments in the galaxy. White dwarfs cool slowly over billions of years. Their habitable zones migrate inward over time, but remain at accessible distances for billions of years. A rocky planet in a white dwarf habitable zone would have access to a stable, low-energy radiation environment for an extraordinarily long time. WD 1856 plus 534b did not prove this is possible for rocky planets, but it proved the vicinity is accessible to planets. There is a detail about WD 1856 plus 534 that has not yet been mentioned. The white dwarf has two companion stars. Not one, two. WD 1856 plus 534 is part of a triple star system, a wide binary consisting of two red dwarf stars orbiting each other at close range, which together orbit the white dwarf at a distance of approximately 1,500 astronomical units. The white dwarf is gravitationally bound to two other stars, both of which survived the death event intact and continue to orbit their dead companion. The existence of these companion stars complicates and enriches the story of the planet's survival. The gravitational influence of the two companion red dwarfs has been acting on the planetary system around the white dwarf for billions of years. Their combined gravitational perturbation at 1,500 astronomical units, relatively weak but persistent, could have contributed to destabilizing the orbits of planets that survived the red giant phase. It could have driven the scattering events that sent WD 1856 plus 534b onto its current trajectory. In a sense, the presence of the companion stars makes the migration explanation more plausible. The gravitational perturbation needed to scatter a giant planet from a few astronomical units onto a highly elliptical orbit that eventually circularizes at 0.02 astronomical units is exactly the kind of perturbation that a distant binary companion could provide over billions of years. The dead star did not die alone. It had companions, and those companions may have shaped the fate of the planet in ways that are only now being untangled. WD 1856 plus 534 was discovered by TESS in 2019 and confirmed in 2020. Since then, the James Webb Space Telescope has turned its instruments toward the system. In 2023, JWST observed WD 1856 plus 534 during secondary eclipse, the moment when the planet passes behind the white dwarf as seen from Earth. By measuring the thermal emission of the system during the eclipse and comparing it to the brightness when the planet is visible, astronomers can extract the thermal emission of the planet itself.
The results were published and immediately noted for what they showed and what they did not. The planet is cold. colder than Jupiter, significantly colder than would be expected if it had recently spiraled through a hot stellar envelope, a result that would seem to favor the migration explanation over survival. A planet that passed through a red giant envelope hundreds of millions of years ago would have had time to cool, but a planet that survived by spiraling through the envelope quickly might retain residual heat from that interaction. The cold temperature is consistent with both explanations under different timing assumptions. It does not definitively distinguish between them. JWST will continue observing the system. Better constraints on the planet's atmospheric composition, if it has a detectable atmosphere, may provide additional clues about its history. The chemical fingerprint of a planet that spent time inside a stellar envelope might differ from the fingerprint of a planet that arrived via cold gravitational scattering. The answer may be in the spectrum. We are still taking it. Our own solar system will face a version of this story in approximately 5 billion years. When the Sun expands into a red giant, the inner planets will be consumed or sterilized. Jupiter will survive. Its orbit, at 5 astronomical units, is far outside the maximum extent of the Sun's red giant envelope. Saturn, Uranus, Neptune, all will survive. Their orbits will shift outward as the Sun loses mass, but they will remain intact as planets orbiting a new white dwarf. What happens to them over the billions of years that follow is not determined. The gravitational dynamics of the surviving outer solar system will evolve. Orbital resonances that are currently stable may become unstable. Planets may be scattered onto new trajectories. Some may eventually migrate inward. Whether any planet in our solar system will find itself billions of years from now orbiting our Sun's white dwarf remnant at a distance comparable to WD 1856 plus 534b, nobody knows. The timescales and parameter space are too vast for confident prediction. But the mechanism exists. The physics permits it. WD 1856 plus 534b demonstrates that the death of a star is not the end of its planetary story. The story continues, reshaped by the death, reorganized by the gravitational aftermath, but continuing. There is a specific feeling that this system produces when you sit with it long enough. WD 1856 plus 534b has been in its current orbit or approaching its current orbit for hundreds of millions of years, orbiting a white dwarf, completing a circuit every 34 hours around the compressed remnant of a star that used to be larger, warmer, more luminous than our own Sun. Whatever process brought it there, survival through the stellar envelope or migration through gravitational scattering, it was not designed. It was not directed. It was physics operating on the matter and energy of a planetary system over billions of years of evolution, producing an outcome that nobody anticipated and that raises questions we have not yet answered. The universe has a way of keeping things, not gently, not carefully, through violence and disruption and the slow operation of gravitational dynamics over timescales that dwarf the history of life on Earth, through processes that destroy most things and leave a few in configurations that were not planned, in orbits that should not exist. WD 1856 plus 534b should not be there. It is there. And in the 80 light years between that system and this one, the difference between those two facts, between should not and is, contains everything we have not yet understood about what survives when stars die. We are still learning to read the aftermath. The planet is still orbiting, every 34 hours, around the star that should have killed it.